Hello students, it's been a week plus since our last literature appreciation workshop. I hope you have read through the article which we left off towards the end. So if you recall our last activity, I got you guys to read for about 10 to 15 minutes of this particular article that I'm showing on the screen, stable controlled synthesis of trichodermatite A, and there's a worksheet with some questions. I hope you have gone through them. So for today's video, I'm going to briefly go through with you the gist of the articles and perhaps also gone through some of the questions in the worksheets. Okay, so if you actually recall how to actually go about reading an article or searching for an article, you will realize that at the very beginning, you should be expecting an abstract, but for this particular journal, Angewandte, there's no abstract in the published article. So where's abstracts? The abstract is actually on the website itself. So if you go to the website, which I'm there right now, so this is the article before that, and then the article itself, you notice that they actually wrote an abstract here. Yep, so people who have read the abstract and then get interested in the article will then just click on the PDF file. So you also realize that there's this corrections for this article. So if you actually click on it, people have the authors have actually wrote in 2 years later to talk about some of the correction that they would like to make to the papers. Yeah, so this is actually quite, I won't say very common, but it does happen in the community. So later on towards the end, I will also go into the correction and show you that actually science is evolving. So the contents you are learning now may not be correct maybe 20-30 years down the road. Okay, so do expect this kind of interesting thing to happen in the scientific community. Okay, so before that, let me just go into the article straight. So if you recall, there's always an introduction like this. So the introduction here talks about synthetic chemistry, so synthesis of natural products. So they mentioned that the routes to synthesis must be as short as possible. I think you can understand why, because it actually saves you on time, raw materials, etc. And then there are a couple of terms they brought out over here. They mentioned that considering this, the development of a method capable of initially providing the core structure of a target molecule followed by the stereo, regio, and chemo selective introduction of function groups, etc. Okay, so you understand what is stereo selective because it's in your curriculum. I'm sure you understand what is regio selective as well. If you don't understand or you forget about them, please go and revise. Chemo selective is a term that's not being introduced in H3, but I'm sure if you do a bit of googling or if you have learn it even in your H2, you realize that it's actually something you have learned. It's just that the term is not being introduced to you. So basically, chemoselective means that one of the functional group reacts to one particular reagent. Okay, so one of the thing I can think of would be say for example in Tollens reagent, right? Versus Fehling's reagent. So Fehling's reagent will not be able to oxidize aromatic aldehydes as compared to Tollens reagent. Yes. So if you have a molecule with an aromatic aldehyde and an aliphatic aldehyde, and you subject it to Fehling's reagents, only the aliphatic component will react. So this is a very clear cut and a common example we use to illustrate to H2 students what exactly chemoselectivity is. Okay, so if you actually read on, they kind of mentioned that the structures of trichodermatite A to D was elucidated in 2008, around 12 years ago, by Pei and co-workers. B to D structures aren't very inspiring, just a few string system, but if you look at trichodermatite A, it has what they call a Panda cyclic system over here. So what exactly is a Panda cyclic system? Well, it can be viewed of as you have one ring here, one ring here, one ring here, and then one ring here, and then one whole ring by itself like this. So this is what we call a Panda cyclic system. And that's probably what got them interested, because the structure itself is pretty complicated. And then if you move on, having a beautiful structure alone is probably not enough. Cytotoxicity against A375S2 human melanoma cells. So if you read about it, these are cancer cells. Okay, so it's, if you have something that is anti-cancer, some structures that has quite unusual structures, then it does warrant the research group to go and find out how they can actually possibly make it in the lab. Okay, so this is something that you might uh, be aware you might want to be aware of when you are reading this kind of synthetic papers, because normally they make molecules that are quite unusual. Okay, so and in this case they actually went on to mention that, okay, this particular structure is 8 carbon centers, and then it contains a ketalic and then ketalic carbon. Okay, these two terms you might not be familiar with. So before we move on and go into reading the rest of the papers, maybe let me just explain very briefly what these two terms is. Okay, so I'm sure you guys know what is a ketone. So let me just draw it out using maybe a blue pen, a blue ink. Okay, so I'm sure you are aware that a ketone looks like this, and aldehyde looks like this. I'm also pretty sure from your H3 curriculum that you are aware, if you subject a ketone and an aldehyde to this particular reagent, in this case, let's say an alcohol, in acidic medium, you would expect this to be formed. Let me just draw it out. Okay, so this particular structure that I drew above, right, is called a hemiketal. The one below is called hemiacetal. Okay, and if it continues to react with the alcohol in the acidic medium, you will get what we call a ketal, okay, and acetal. Okay, you'll be wondering what's the point in talking about all these structures, right? If you're a biology student, you study carbohydrates, etc., you realize that a lot of carbohydrates have structures that looks like either a hemiacetal, hemiketal, a ketal, or acetal. Okay, so one of the examples that I can think of for you right now will be in the article. If you just go straight into the article, you look at trichodermatite, right? Are you able to point out to me where is the ketal? Okay, so if you are able to, it's actually right here. This is a interesting structures. So if you think about it, this is one of the reason why they want to go about synthesizing it, because in actual fact it's not so easy to make it the way you wish it to be made, because there are a lot of possibilities, that a lot of combinations you can get, but of course some combinations are not exactly thermodynamically favorable as what they have described in the paragraphs, if you actually read on. Okay, so and then if you move on, they actually talk about this. It's a ketal formation, uh, cobalt catalyzed hydration reaction to innovator. So they are pretty descriptive in what they want to share with you, which is pretty good. Okay, then as we move on, if you look at the next half of the first page, they talk about, for the synthesis of the core of one, we plan to use ketal exchange and dehydrative pyrene formation. So again, pretty bombastic term. Now you understand what's ketal, and so ketal exchange, probably you will be able to understand it a little bit more. Okay, and dehydrative pyrene formation, dehydration, you know what's dehydration. Pyrene, you might not know what a structure of pyrene is, but you can just Google and then you realize that it's actually a 6-member ring of oxygen. Okay, both of which can be promoted under acidic conditions. So yep, so they start off from a dimerized 1,3 cyclohexane dione derivative 5, so it's here, and then again H plus with a ketal exchange. You might be wondering, earlier on in my examples here, I have the alcohols, right? If you can see from what I've drawn for you. So I have the alcohol starting material here. Then and then it ends up here, 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 and here. Then you'll be wondering, so in this case, where is the alcohols and where is the ketones? Well, if you actually recall, if you look at this particular ring, this 5-member ring, right? Yeah. So let me just show you. So this 5-member ring is actually quite common as a structure. So if I have this ring that looks like this, okay, don't you think that it actually sort of resembles what we have above? Don't you think so? What we have above, it's okay. So that's what we actually call hemiketal, right? Okay, so I mean the structure looks a bit weird the way I drew it, because it's a bit difficult to draw freehand on the computer screen, but yeah, so it is the way it is. So so if you are able to actually see it, then you realize that the above structure, after you have done something to it, you are able to actually recreate the ketone. So from here, it is actually possible for you to get the ketone out, right? So in this case, you generate 2 alcohols, and then the 2 alcohols will then continue to react with this part and this part. Yeah, those 2 arrows I've drawn, they are actually called the mask ketones. So remember, that is actually the enol form. Okay, so if you recall from what you have learned in your H3, the enol form can be interconverted into the keto form. Okay, so if you're not sure what I'm talking about, it's okay. You can just read a little bit more about them, but I need to move on with what I need to cover. So there are a lot of possibilities. So 5 can go all the way to 6, 7, 8, 9, 10, and 11. Okay, but very interestingly, they use pretty interesting terms, the authors. They call 10 to 11 what they call the potent intermediates. So, and actually they actually describe to you why they call it potent intermediates. Over here they actually said that they are formed under thermodynamic conditions, and they have previously discussed a method to form chiral quaternary carbon center. Okay, so that's something they did previously. But what is interesting is that they mentioned that 10 and 11 are potent intermediates, and later on you'll realize that 10 to 11 actually is able to lead to the pentacyclic core of trichodermatide A. And they also mentioned that 10 and 11 are thermodynamic products. Later on, if you read the second page, you'll recognize why is that the case. Okay, so I will leave that for a later discussion. And then the next paragraph, they mention, for the basis of this strategy, the synthesis commences with the preparation of aldehyde 12 and blah blah. Start from tartaric acid with well-known procedure, and then if you go to my questions, the first question that was asked is why tartaric acid is used as the starting material to synthesize 12. If you take note of the tartaric acid, you realize that it has 2 chiral centers that are already formed. Do you recognize that? The 2 chiral centers are already formed. And then if I go back to the next synergetic scheme over here, you realize that 12 also has 2 chiral centers. Okay, so why is it important to start off with a chiral starting material? Well, I'm sure you are aware that if I can start with a chiral starting material, I do not exactly need to worry about how my 2 chiral centers will be formed in the next few steps. So starting from tartaric acid really helps a lot, and tartaric acid is really cheap. If you just Google it, I think it costs around a couple of hundred USD or less for like a couple of kg. Okay, so that's really quite a lot of it. So you can actually buy a lot of tartaric acid for free, not for free, but with a very low starting price. So in that, or if you are interested enough and you are adventurous enough, you can actually make your own alpha acid. It's not really, it's not exactly too difficult to make. If you just Google, I think you can easily find a way to make it. But of course, most research lab, they just want to start off their uh, research fast, so they just buy the alpha acid. Okay, so the next thing we're going to go on is to continue reading it. Okay, you discover something really interesting. They actually mentioned that I think this part onwards, the key synthesis steps which involved the diastereoselective formation of the ketal 5 was the initial attempt to reflux benzene with p-toluene sulfonic acid, PTSA. And then they mentioned that unfortunately the isolated compound was not one of the anticipated 6 to 12, but was the unexpected 13. So what exactly is 13? So 13 is this ugly looking 7-membered ring, okay, fused into 6-member ring, and then the other 2 6-member ring on its sides. Okay, so later on you'll discover a little bit more. Okay, so unfortunately, however, okay, sorry, we read that. So what's next? Okay, over here, in contrast, reaction of with 5 with a weak. Okay, so they say weak pyridinium para-toluene sulfonate resulted only in the formation of 9 substituted 9-hydroxyl the ring, and then represented by the conversion of 5 to 14. Okay, so the weaker PPTS gives you 14. Okay, but the stronger acid straight away give you 13. Right. So in this case, of course, we want to get 14, but not 13. Okay, then later on they mention, oh, furthermore, the reaction of 14 under the same condition in the presence of PTSA give 13 in 60% U. Okay, so so I hope this particular paragraph throws some lights into how people actually do research, and that's something you could probably learn from here. Okay, you realize that when they 14, but they don't stop there. They want to add PTSA in and then to see if they can get 13. But when you add PTSA directly, you get 13. So from here, they kind of able to draw the conclusion that in order for me to form 13, 5 must go through 14 before 13 is formed. So that's kind of like an interesting way of rationalizing it. And later on, if you read more, they actually went on to do quite a bit of discussion on that. Yeah. So sometimes by reading research paper, you get to learn how scientists actually think through some procedures, and you get a logical thinking behind why they are doing certain things. Okay, and okay, so I think it's a good juncture for me to go straight into this. Question 2, explain why PTSA is a stronger acid than PPTS. So this is a very good visit to your acid-base equilibrium you learned in your H2. So I think we can go into that. Well, if I say that PTSA is a stronger acid, that means that the conjugate base, which looks like this, the conjugate base, oops, sorry, that's not meant to be so big. Okay, let me just erase. Okay, the conjugate base, okay, let me just use a blank space below. The conjugate base looks like this. Okay, with the negative charge on the oxygen. Okay, you realize that the negative charge on the oxygen is next to 2 electron withdrawing group, S11O. So in that case, the negative charge will be largely diminished in terms of intensity, or you can say it might be resonance stabilized. But in the case of PPTS, the conjugate base is actually pyridine. That looks like that. Sorry, just ugly structures here. Okay, just let me erase and then draw properly. The conjugate base is actually pyridine. And if you notice, pyridine has the lone pairs of electrons here that is in the sp2 hybrid orbital and is orthogonal to the pi electron cloud, so it's not delocalized. So that makes the conjugate base, which is pyridine, a much stronger conjugate base as compared to the sulfonates. So in that case, you would expect PPTS to be a way weaker acid as compared to PTSA. Okay, because in terms of conjugate basicity, pyridine is definitely more basic. Okay, so you realize that, I hope at this point you realize that a lot of the knowledge you learn in your H2 and H3 can actually help you to unpack a lot of things in research papers without you knowing, to be honest, without you knowing. Okay, because without me explaining to you that, hey, you actually is able to understand some of these things, you might not even be aware that you are more than capable to do that. Okay, but of course there are a lot of terms that you are not aware of, and if you're not aware of those terms, then obviously you need to Google, or you just need to dig them out from some textbooks. Okay, so anyway, I'm just going to continue. Right, so from here on, you realize that after getting 15, so after getting 15, they subject it to the weaker acid, which is PPTS, and then they are able to get 11. Okay, and then of course when they subject 11 to the stronger acids, they get something else, which is 16, etc., and then eventually 13. So they actually went on to study, and after they have studied it, they begin to understand why they are able to get one over the others. Okay, right, so, and okay, now if you look at scheme 2, right, you realize something interesting. They show you the conformation of 11 and 9, and 11 shows you what you have here is actually a chair conformation, and 9 is actually a boat conformation. And from here, let me just go back to the previous page, right? Are you then able to explain to me why at least 11 is favored over 9? Okay, think about it. Are you able to explain to me now? And after they have drawn for you the chair conformation of 11 and 9, or rather 11, and then the boat conformation of 9, are you then able to, based on the drawing that they have provided you, draw for me the conformation of 10, 8, 7, and 6? Try it. Okay, try it. Yeah, because that is one of the questions that I didn't ask you in the worksheet. So I thought it's a very good practice for your conformational analysis. Okay, so try it out, and yeah, we'll release the answer to that later on. Okay. Okay, then moving on to that. Okay, yeah. So after that, it's not very interesting, to be honest, because this author is tend to be a bit descriptive in his in the way they write it. So after that, it's a lot of explanation over here. So it actually went on to describe to you what exactly happened, like which OH reacts with which carbonyls, and then they did some studies. Okay, so I won't go into all those details, and then more and more description, and then they realized that, okay, one conformation is better than the other. So whatever I've sort of mentioned to you is covered all the way until here, and then after that I've covered something else in front. I'll sort of mention about the 11 as a transient intermediate, or rather 13, 11 as a transient intermediate. Okay, and then before you get onto something else, yeah, that's how they study it. And then what is important is actually, or rather something that they have really found is really important, is actually over here, which I've drawn 2 lines in yellow. So they mentioned that the formation of ether 13 from 11 through a 7-membered ring cations intermediate by an energetically unfavorable CO bond activation by PTSA. Okay, so if you are able to, I want you to think about how can this take place. Why is this so-called unfavorable? Which is quite interesting point that they raised. Yeah, so sometimes they might have written some things that might not really be the 100% truth, but it's really what they think, because from experience this is how things go. So if you are able to, you can think about why is that CO bond activation unfavorable, and how come it can only be activated by a stronger acid. Okay, yep. So you realize that actually a lot of the reaction or even the side products, they are actually being formed from a different mix of OH with a different carbonyl. Okay, so if you do recognize this, you realize that I'm talking about 5. Okay, let me just use red and then I zoom a little bit more so that it's clearer. You realize that this is actually a hidden carbonyl. Okay, and when you are actually going from 5 to 11, right, this and this O, right, eventually will become the OH actually reacted, and they get this over here. Okay, this particular carbonyl remains intact, right? Now if you notice about 13, right, it's interesting. Only one of the OH reacted with the carbonyl earlier on. The other OH actually reacted with this carbonyl. Yeah, so that's what they are trying to say. And that's the difficulty that they faced. Which I guess you have to read a little bit more in detail to understand the difficulty they faced. And then why do they get one over the other in different conditions? Okay, so that's the interesting thing that they are trying to describe to the reader throughout the whole um, papers, at least until here. Okay, that's the stuff that they're trying to describe to you. Okay, after that is not so interesting, I would say. Yeah, because after that is really pretty descriptive. So I will just very quickly go through them. Okay, so after that they mentioned that the remaining task was basically to introduce the 3-hydroxyl group in the correct positions. So where are the 3-hydroxyl group? So again, I need to go back to the first page. Okay, so the 3-hydroxyl group, this secondary alcohol, this tertiary alcohol, and this secondary alcohol. Okay, so these are the 3-hydroxyl group. And if you have read it and you remember, the way they introduce it is really one by one, which is not very inspiring, but I guess given the current situation, that's the best way they can do. Okay, so yeah, so if you read through everything, basically this is what they are doing now. Okay, so first they try something interesting called allylic oxidation. So if you're interested, you can read about it. So what exactly is allylic? So let me go into this. So basically, if I have alkene and then a CH2 here, so carbon 1, 2, and 3, right? So carbon 3 is what we call the allylic carbon. Yeah, it's just called the allylic carbon. And normally, if you control the condition, right, the allylic carbon is quite susceptible to reaction. So it can be oxidation, it can be halogenation. Okay, so that's what they are trying to do here. So they are actually doing allylic carbon oxidation. Yeah, yeah. So after this it gets a bit descriptive because they went on to say that, oh, okay, they get 17 in not so good yield, 15%, but they only managed to recover 11 in 20%. So what's the remaining stuff? They didn't really say. And then they went on to say, okay, to the best of their ability, they got 17 and 15%. They try and try. That's all they can get, and they can't move beyond that. Yeah, and what do I mean by they can't move beyond that? Meaning from 17 they can't move on. So they realize they're stuck. So since they are stuck, what do? They change their strategy a little bit. So instead of doing a late oxidation on 10, they are doing a selective oxidation on carbon 2, which is being activated by the carbonyl group. Okay, so this is carbon 2. So they did an oxidation on carbon 2 using an interesting reagent called a Davis reagent. So I think it's mentioned here. Davis reagent. So it's mentioned here. So they use this is the Davis reagent. Okay, so after that they managed to get the oxidation in place. They get the OH in, and then they introduce a interesting reagent, this reagent in, and then they got this whole group in, which is being shown here. Okay, so obviously this nucleophilic acyl substitution. Okay, so after they have gotten it in, then they did their allylic oxidation, which got the OH into that position. Okay, so they changed the procedure a little bit, which is actually okay. I mean, sometimes research is trial and error, so don't get too upset if one way doesn't work. Yep. after that they gave a little bit of description like, okay, why one of the diastereomer is not detected, but later on you realize that there may be some error, okay, but not exactly error over here lah, but we'll describe that later. Okay, so yeah, after that it's not so interesting anymore. They tell you more and more stuff, but finally the third hydroxyl group is really the problematic one. They didn't really go into a lot of details how problematic it is, but they just tell you that, after several efforts they discover this interesting cobalt catalyzed hydration developed by Izayama and Mukayama. Okay, so basically it's from 22 alpha and then go to 20, 23, 24, and then 25. So it's a it goes via a radical base mechanism. Okay, so it's a radical base mechanism using cobalt. And if I would ask you a question, how come oxygen can react with the radical, I'm sure you will be able to tell me some stuff lah, because oxygen is existing as a diradical based on what you have learned under MO. So as a diradical, it can easily undergo radical base reaction. And then they also went on to say, to actually sort of explain how come the other double bond, which is over here, this double bond, how come the other double bond is not reacted. Okay, so they need some explain why the other double bond remain intact because of the electron withdrawing C double bond O. Okay, so anyway, we don't go into details, and then after that they talk about this, the origin of stereoselectivity, etc., etc. Later on they actually did say that um, this might not be entirely true, but we don't go into details lah. Okay, then and that's about it. Yeah, I think that's it. Okay, so they said, to the best of our knowledge, this is the first attempt of application of cobalt catalyzed hydration reaction to an innovator. Okay, so yeah, I mean, you might be thinking, so what's so inspiring about that? Uh, Probably because most of the time innovator doesn't undergo this kind of reaction. Maybe, I'm not sure. Okay, so and that's it. And then they have a summary. So of course the summary tells you the gist of what they have done. So basically they say, oh, it started with L-tartaric acid. Okay, highly efficient intramolecular ketal formation reaction. So focus on the pentacyclic core by controlling 2 of the 8 stereogenic centers. And then they said the additional strong short sequences, including cobalt catalyzed enohydration, successfully functionalized the core 1 by controlling the remaining 4 stereocenters. Okay, that's fun. That's fair lah. Then, if I go back to my question, I actually asked you the last part. That yeah, it's novel, it's pretty short, highly efficient intramolecular ketal formation, but it's not without its shortcomings. So in your opinion, what do you think are the shortcomings? I'm not sure whether at this point in time you have thought through it, but if you actually recognize the whole story, the part that is not so nice, I feel, is really the 1 by 1 addition of the OH. Yeah, I think the formation of the pentacyclic ring is beautiful. Like, things goes on really well. You get a thermodynamic product. Everything is beautiful chemistry. Pretty much what you have learned in H3. Yeah, but what is not so nice is actually the fact that for the OH, they actually added in 1 by 1, which again, yeah, doesn't seem so beautiful. But I think it's okay. It's still a good paper. Still a good synthesis, because I'm sure from the writing of the authors, there's a lot of things that you can learn from it lah. So like they learn from their failure as well. For example, you see how they do research when they try to get 11, and then they try to see if from 11 they can get 13, right? And then from scheme 3 earlier on, I mentioned they wanted to do the allylic oxidation first, but they realized that they can't go anywhere from 17, so they decided to do the oxidation on carbon 2 first before the allylic oxidation. Yeah, so really this is kind of try and error, and this is really how research is like. And in the remaining 1 or 2 minutes, I'm just going to show you the reality of research, okay, so that you are really aware of what exactly is going on. So the reality of research is that people do make mistakes, and these are honest mistakes. Okay, so 2 years later, I think over here I did show you, right? There's a correction of this article 2 years later, right? So I happen to have it here. They actually publish a corrigendum. So a corrigendum is like something that they want to correct it in a publication they had earlier on. So let's read a little bit. So this publication by Troner Group is actually a German group, prompted the authors of this communication to make structured assignment by re-examination of the animal experiment for the synthetic trichoderma type A. So what they are trying to say here is that, oh, okay, actually after they have seen the publication by Troner's group, they realized that, hey, you know, what they had assigned earlier on might not be correct after all. So remember earlier on, a key aspect is this cis configuration over here. So if I just go back to the original paper for you to see the cis configuration, yep. Then they realized that, oh, actually it should be the trans. Yeah. Then after that they went on to actually correct everything. So yeah, people can make mistakes, and research is really ongoing. A lot of knowledge is new. So if you make an honest mistake, it's okay to correct it. Yeah. So these are really real stuff. Okay. When they publish a corrigendum, it's probably something that they feel that the research community should really recognize that they might have made an error. Okay. And there might be something that I didn't really mention in our late appreciation workshop, but for every research paper there's something called supporting information. So let me show you the supporting information of this research. So this is their research paper in 2013. This is the what we call the supporting information. Supporting informations are like spectra or other experimental details that were not included in the writing of the paper, because those are really details that you don't need to know in order to get a full picture. Okay, so these are usually, let me just show you what they are. Okay, so in this case they have a table of contents. So you can see that from the table of content you can see that, okay, this is the compound, this is the procedure on page 1, this is the 1H NMR on page 10, and then on page 13 is the carbon 13 NMR, and then they have even done 2-dimensional NMR because they feel that there's a need to. Okay, so I just briefly show you what is it like. So these are the procedure. You see it's written like this. It's a very simple procedure, quite different from your lab experiments. And then usually they do IR, melting points, 1H NMR, and carbon 13. Mass specs and high resolution mass specs as well. Okay, so these are the standard stuff that needs to be in before you send something for publications. You might be interested in the spectrum, so just go straight to the spectrum to show you. Okay, so the spectrum looks something like this. Yep, this is a 2-dimensional NMR, and then this is a carbon 13, and then this is the 1H. Yeah, you can see it's really complicated, and because the molecule is very big. Okay, so yep, I think that's about it for the papers. I hope after I've explained to you, you guys are clearer exactly as to what this paper entails. Okay, so the next thing I'm going to do will be to discuss some of the questions that you have in the worksheet. I think the remaining questions are those mechanism types.